torsion as a second geometric degree of freedom, quark spin structure, and the proton spin crisis. Experimental investigations of proton structure have revealed that the intrinsic spins of quarks account for only about 30% of the proton's total angular momentum. The remaining contribution is generally attributed to gluon spin and to orbital motion of quarks and gluons within the framework of quantum chromodynamics. Although this distribution is broadly consistent with the theory of strong interactions, the detailed decomposition of proton spin remains an active area of research. This essay explores a speculative but conceptually motivated question: whether a portion of angular momentum associated with intrinsic spin could be encoded in geometric structure rather than entirely within matter fields. The investigation begins from the geometric interpretation of gravity established by General Relativity, in which gravitational phenomena arise from the curvature of geometry. In this framework, mass energy acts as the source of curvature, establishing a precedent in which physical quantities are represented by geometric degrees of freedom. More general geometric connections allow an additional structure known as torsion. While curvature measures the bending of geometry, torsion measures a twisting of the connection. In extensions of general relativity, such as Einstein-Cartan theory, torsion couples naturally to intrinsic spin. Mass energy therefore sources curvature, while spin density sources torsion. In minimal formulations of Einstein-Cartan theory, torsion is algebraically constrained and does not propagate independently. In non-minimal formulations of Einstein-Cartan geometry and related extensions of gravitational theory, however, torsion can behave as a dynamical geometric variable. In such cases, curvature and torsion represent two distinct geometric degrees of freedom associated with the connection structure of geometry. This distinction raises an interesting possibility. If intrinsic spin couples to a torsion sector of geometry and torsion possesses independent dynamics, then angular momentum associated with spin may not be confined entirely to matter fields. Instead, some portion of that angular momentum could be encoded in the geometric configuration of the torsion sector. The proton spin problem, therefore, provides a natural context in which to explore this idea. Rather than viewing the remaining angular momentum of the proton solely as a redistribution among quark and gluon degrees of freedom, one may ask whether part of that angular momentum might correspond to excitation of a torsion sector generated by quark spin. The proposal considered here does not challenge the conventional explanation offered by quantum chromodynamics. Instead, it suggests that some portion of what is currently attributed to field angular momentum might correspond to geometric degrees of freedom associated with torsion. In this interpretation, intrinsic spin acts as a source for a geometric torsion sector, in much the same way that mass energy acts as the source of curvature. The discussion is situated within a broader operator-based geometric framework, in which the fundamental carrier of physical structure is a dynamically evolving spatial geometry. In this ontology, time functions only as an ordering parameter, rather than as a state-bearing dimension. Physical persistence must therefore reside in geometric variables of the carrier itself. Within such a framework, torsion provides a natural candidate for storing geometric residue associated with intrinsic spin. Although this interpretation remains speculative, it highlights a potentially interesting connection between hadronic spin structure and geometric gravity. The central question motivating the essay can therefore be stated as follows. If intrinsic spin couples to a torsion sector of geometry while mass couples to curvature, could the proton spin crisis represent the first empirical hint that part of angular momentum is encoded in geometric structure rather than entirely within matter fields? Addressing this question would require further theoretical development and careful consideration of experimental constraints on torsion. Nevertheless, the possibility that angular momentum may be partially represented within geometric degrees of freedom invites renewed exploration of the relationship between spin, geometry, and the structure of gravity.